Okay, I think we're good to start here. So thank you so much all for joining. This is the third webinar in the Concourse webinar series, and we're very excited to have today Dr. Sylvia and Maziar walk us through some of the latest research they've been working on the decarbonizing concrete. You could go to the next slide, Maziar. First of all, we respectfully acknowledge the space that the Concord is headquartered in as the traditional territories of Treaty 7, comprising the Blackfoot Confederacy, Siksika, Piikani, and Kainai nations, the Stoney Nakoda nations, Goodstoney, Chiniki, and Bearspaw First Nations, and the Tsuut'ina nations. These lands are also home to the Otempisuak Métis government, districts 5 and 6, and these acknowledgements are some of the beginning steps on a journey of several generations, and we share them in the spirit of truth, justice, reconciliation, and to contribute to a more equitable and inclusive future for all society. And personally, I'm joining from the ancestral territories of the nations 13 here in Toronto. Okay, so moving on, my name is Luisa Corredor. I am the CDR analyst at the Femina Institute, and I'm super excited to be joined by two experts from the University of Calgary. We're all part of the Concord Initiative, which is a multi-organization project that aims to assess the potential of carbon dioxide removal technologies to meet Canada's 2050 net zero goal and to identify policy options that could enable sustainable, equitable, and rapid deployment of CBR in appropriate context. What is very cool about this initiative is the breadth of disciplines that it encompasses, from political science to physics to law and engineering. Overall, there are 25 faculty and staff involved, and this is all made possible by support from the Environment and Climate Change Canada, as well as Natural Resources Canada. We have it there, but various universities are participants of these initiatives: the Simon Fraser University, University of Alberta, University of Calgary, who is leading it, the Femina Institute, and the University of Toronto. And moving on. Maziar, you might go into the next slide. I am actually very excited to present you the two experts that will be talking with us today. First, we'll have Dr. Sylvia Sleep. She's an assistant professor in sustainable systems engineer and civil engineer at the University of Calgary. Her research focuses on the development and integration of system tools, including life cycle assessments, techno-economic assessments, and energy systems modeling. All of this to develop prospective assessments of new technologies and their potential to play a meaningful role in decarbonization. Current focus areas include development of the industrial sector in a Canadian open energy model using a TEMA framework, developing methods for improved assessments of early stage technologies, and integrations of ECA. TIA and geospatial modeling tools to assess the potential benefits and trade-offs associated with deploying new technologies, including low carbon hydrogen, carbon capture, utilization and storage, and carbon dioxide removal technologies. Maziar is a PhD candidate at the University of Calgary, where his research focuses on carbon capture, utilization, and storage in cement and concrete as part of the Concord Initiative. His work evaluates technology pathways to achieve net zero concrete production, and Maziar also holds a master's degree in environmental engineering from the University of Tehran, where his thesis focused on the life cycle assessment of concrete. He also has a bachelor's degree in civil engineering from the University of Shiraz. And with that, I'll pass it over to Sylvia to take it away.
Yeah, thank you, Luisa, for that introduction. So to set the stage for Maziar's talk, today I'm going to give a brief intro to the life cycle of cement and concrete and talk about why we're focusing on it within Cancor as a potential pathway for deploying CO2 mineralization in Canada. So annually, we produce about 4 billion tons of cement, which is used to produce about 14 billion cubic meters of concrete that's responsible for about 7% of our global GHG emissions. This is expected to increase to about 20 billion cubic meters by 2050. So if we're going to meet our net zero goals, we really need a plan in place to decarbonize this sector. If we look at where emissions come from across the life cycle of concrete, we can see that the majority, about 80 to 90% of those GHG emissions, come from the cement manufacturing stage. Cement is made from taking limestone or calcium carbonate and heating it up in a kiln to about 1400 degrees Celsius. This process, known as calcination, produces calcium oxide, which is then ground and mixed with other materials to produce cement. Cement is then mixed with aggregates and water to produce concrete. If we were to install carbon capture anywhere across the life cycle of concrete, it would be at the cement manufacturing stage, where emissions come from both the calcination reaction and the fuels combusted to heat the kiln. Concrete, if we look further down in the life cycle, if we could go back, thank you, also has the capacity to absorb some CO2 over its life and during the demolition and disposal phases, partially offsetting the release, the CO2 release during the calcination process. This is one of several pathways where we can see mineralization in action, albeit very slow action within this sector. Next slide. So what is CO2 mineralization? Carbon mineralization is a process that naturally occurs over hundreds or thousands of years in which minerals inside rocks react with atmospheric CO2 to create carbonates. It is very similar to the reverse of the process by which cement is made from limestone. This chemical reaction works best with rocks that contain alkaline minerals like magnesium or calcium-bearing silicates, which are reactive with CO2. These can include minerals within certain rock types, also present in mine tailings and industrial byproducts. CO2 mineralization naturally sequesters about 0.3 gigatons of CO2 from the atmosphere. And we also have mechanisms in place by which we can accelerate or enhance that process to increase the amount of CO2 that we are carbonating. This is a process that also occurs within the concrete that we see and interact with every day. So concrete's actually quite porous and has these tiny air gaps through which CO2 from the atmosphere can enter into the concrete and react with calcium-rich products within the concrete itself, becoming sequestered in the concrete in the forms of carbonates. Over the life of concrete in, say, a beam or a concrete block, this will partially offset those emissions that are released during cement manufacturing. How much is naturally taken up by the concrete depends on the exposure conditions of the concrete, the type of concrete that was used, and other factors. Next slide, please. So the work that Maziar will be presenting today is one part of a larger project within Cancor to evaluate the potential for enhanced mineralization across a range of industries that mine and transport large amounts of rock. So working with researchers at the University of Alberta, we're assessing the potential for mineralization in the mining, cement and concrete, and agricultural sectors. This work includes three main components. The first is lab work to estimate the CO2 drawdown of different minerals in the Canadian climate. We're using the results of that lab work to inform the LCA's and TEA's life cycle assessments and techno-economic assessments of different mineralization pathways. The third part of the project is to integrate those LCA and TEA results with maps that include Canadian transport networks and available mineral deposits to assess the potential for CO2 mineralization across Canada, considering transport and mineral availability constraints. And now I'll turn it over to Maziar, who will be presenting the results of a study where we evaluate how different mechanisms for capturing and using or storing CO2 from concrete compare from a life cycle perspective.
Thank you, Sylvia. Hello, everyone, and thank you all for being here. My name is Maziar Javadpour. I'm a PhD candidate at the University of Calgary, working with Drs. Sean McCoy and Sylvia Sleep as part of the Cancor initiative. And we focus on carbon capture and utilization in concrete. Now, every 2 seconds, somewhere in the world, even though concrete is poured, enough concrete is poured to fill an Olympic swimming pool. It's the second most consumed substance on the earth after water, and it's responsible for about 8% or 7% of global GHG emissions. Today, we're going to be talking about why this challenge is so complex, and more importantly, what we can actually do about it. And to understand that, as Sylvia mentioned in her presentation, we need to go over the concrete's life cycle from cradle to grave. And going over concrete life cycle from it starts from raw material extraction. Now this is the part where we mine the limestone and other materials. Then we move to cement and concrete manufacture. Then we start the useful life of concrete. Then, which is also marked by the demolition. The end of it is marked by demolition, where we have the disposal and the end of life of concrete. But the main part is well, the cradle to gate. This is where the root of the problem is, and as Sylvia put it, the calcination of limestone. Now, to break down when we make cement, we heat the calcium carbonate. This breaks it down to calcium oxide or lime plus CO2. This is about 1/3 of cement's emissions, and this is what fossil fuels is really getting us. Then we take this lime and combine it with other materials and we make clinker. But during this process, you can see the equation on the screen here. We have a fundamental chemistry problem. Making cement inherently produces CO2, right? And it's not just about the energy that we use to heat the kiln, and even though that matters too, it's the chemical reaction itself that releases carbon. And this is what makes concrete such a hard to abate sector. And this is where all the problem really comes in. So how can we, or are there actually no ways of solving this? Well, the solution, we do have some solutions in place. We have tried approaches in the past. It's not like we never had any solutions for this. Well, the first solution is the alternative fuels. We can replace fossil fuels with lower carbon options, but there's a limit to how much this helps because of the calorific content requirements of the fuels that we use for cement production. So we really can't take all of this 1/3 of our emissions and just remove it entirely, because we'll probably need fossil fuels as we want to make cement because of the calorific content requirement. And the second solution that we have for this problem is reducing the clinker, which is the main constituent of cement, right? And reducing the clinker, we can use something called a supplementary cementitious material, which is well, going to act as if it's cement. So it's very similar in terms of how it can react and it can bind particles together. But at the same time, it doesn't have the calcination of limestone in its production process. So it's less carbon intensive. But then we really can't take out all of the clinker either. So we might be able to take out a percentage, a fraction of the clinker. Now, depending on what is the replacement that we're using, we can take out different amounts, but we can never fully take out the clinker from the process itself, which means that, well, we have limitations on our emission reductions. So what next? What solution is next on the menu? Well, one of the best solutions that we have, and this really is where the biggest reductions could probably be happening, is in carbon capture and storage. So in carbon capture and storage, we can retrofit it, or we can add it to cement plants that are being built, and we just take the CO2 that is being released, whether it's from the fuels that we are burning or whether it's from the reaction itself. We can just take all of that CO2, well, not all of it, and just capture that and then geologically store it. But CCS has its own challenges as well, right? It has an additional energy requirement. So we need to consume more energy to do CCS. That means that, well, potentially we are releasing more CO2 somewhere else. And local CO2 storage isn't always available. Sometimes it's just not available in the geological formations nearby because you need the right geology. And sometimes it is, but it's expensive. So you might have to like ship it offshore and similar problems. And these aren't insurmountable problems, but they do limit how quickly and how broadly we can deploy CCS for cement. But this is, again, where we probably see the most substantial reduction in emissions. So we talked about these. Now, the scientists looked at this fundamental problem with CCS and it being the cost and the, well, getting rid of the CO2 that we've captured. And they looked at the concrete's life cycle to see a solution for the captured CO2. So instead of just capturing CO2 and storing CO2, what if we could use it? And two promising pathways within the concrete production chain and the focus of our webinar today are, well, carbonation curing and mineral carbonation, which we'll get to them in just 1 second. So the scientists look at the concrete life cycle chain, and they saw that concrete has this remarkable ability to absorb CO2 from the atmosphere during its useful life and end of life. So they thought, well, what if we put all that concrete in this chamber and then we expose it to concentrated CO2, which will react to the cement and gets permanently locked into concrete, right? And it might or may not, depending on how we do it, actually improve concrete properties. The second pathway is mineral carbonation. Now, mineral carbonation, we take the CO2 and we react it with minerals rich in calcium or magnesium silicates to produce a supplementary cementitious material, which, if you've forgotten, those materials that we replace clinker with. And in this case, it's silica, amorphous silica, that can reduce the clinker content in concrete while also sequestering CO2 within that process, right? So now, instead of just taking that CO2 and then dumping it somewhere underground, we have uses for CO2 within the concrete life cycle in itself. But it's not as straightforward as that, unfortunately. Both of these processes require energy, and a lot of energy sometimes, depending on which process we're actually going with. And remember how remarkable ability to absorb CO2 during its useful life and end of life. Now, it turns out if we do carbonation curing, we're actually limiting that potential, right? Because concrete does not have this infinite capacity to store CO2, right? So if we do more in our cradle to gate, in our manufacturing stage, that means that the concrete will absorb less further down the road, right? So that's something that we need to keep in mind. And we do have other problems here as well. We have, other than the energy consumption increase, we also have an increase in the transportation, because now we want to do mineral carbonation, let's say. We need to transport minerals to a facility where we do the mineral carbonation. Then after we've expanded our energy to do the mineral carbonation itself, now we have the silica that again needs to be transported. Now, which this, of course, is not like a big problem, or it might be, we don't know yet, but it does add some complexities to the problem. So we need to just take care of that. And of course, there's costs, right? Like we have the capital costs and operational costs. And so this is the outline of the potential solutions that we've really put out here. And before we can implement any of these at scale, we need to answer some critical questions, right? All of these challenges, the energy consumption, the logistics, the cost, everything, these are not just technical problems. They have real environmental and economic implications. And this is where we need rigorous analysis to come in to really answer these questions. And to do that, well, some of these questions are better answered through life cycle assessment, and some of them are better answered through techno-economic analysis. And sometimes even both of them together. But our focus today is on the life cycle assessment part. Now, in our life cycle assessment, we focus on 4 key areas for carbon capture and utilization: the added energy consumption, the added energy for utilization of this CO2, the natural uptake reduction that happens once we do carbonation curing, and the added transportation. And then we put them all on one side of the scale, and we put the benefits that we get from carbon capture and from carbonation curing, the increased uptake, and the reduction in clinker content on the other side of the scale, and just see what goes on here, right? But before we get into that, we need to zoom in on the natural uptake question because it's more complex than it might seem. Carbon uptake depends on both internal and external conditions, and as Sylvia put it. So higher porosity, talking about internal conditions, higher porosity and lower strength concrete is generally going to take up more CO2 during its life and end of life than a more stronger concrete and a higher compressive strength concrete because of how denser the stronger concrete is. And of course, external conditions also play a huge part. Imagine a concrete that is placed in this room where we all live or where we work. There you would have a higher CO2 concentration. Because the concrete is exposed to this elevated concentration of CO2, of course, it's going to take up more CO2 as opposed to a concrete that is placed somewhere in the nature and out in the vines, right? So this is just something that we need to take into account. Now, here's what the data and the model that we did actually shows. These two graphs that you can see here are comparing two different concretes that are different both in internal conditions, which is the compressive strength. So the graphs that you see on the left, the bar chart shows the 15 MPa concrete versus the 30 MPa concrete, the higher, stronger concrete on the right. And we can also see the environmental conditions that they're put in as pessimistic, mid, and optimistic. And this is optimistic for the carbonation. So optimistic means a exposure to higher CO2 concentration and etc. So, and if we take a look at these, we'll see that every one of them have two bar charts associated with them. One is natural and the other one is cured. And in every case, we can see that, well, once we cure our concrete, we actually see an increase in the CO2 uptake, which is good. That's something that we want to see when we look at these utilization pathways. And but the issue is here. Let's assume that we have 18% of carbon uptake during our carbonation curing. And that means that we claim this benefit. The green arrows are what we actually would claim. But the actual benefit that we would get is these orange arrows, because as you remember, when we talked about that remarkable ability of concrete and carbonation curing, but carbonation curing will decrease the carbon uptake during the end of life and service life. So what we really see and what we're facing with when we talk about carbonation curing and claiming credits is this little overestimation, these red arrows that you can see here. And this is something that we need to be very, very careful about. So now that we know a little bit about the carbonation curing and natural uptake, now let's take a look at the full life cycle results comparing different scenarios. And so here we have the prospective technologies, CCS, carbon capture and storage, carbonation curing, mineral carbonation, and the incumbent practices, which are both no carbon capture, steam curing, and no mineral carbonation, of course, right? So steam curing is what we use right now, especially for concrete blocks, which carbonation curing is really targeting. And this is our incumbent practice for both of the concretes that we saw before, the 15 MPa and the 30 MPa. And of course, as you can see, the 30 MPa has a higher cement content. That's why you can see a higher number associated with the 30 MPa, the 43, and the other one is 27. So as we go and implement more and more of these CCS technologies, we see this general trend of reduction in emissions. And of course, this is what we expect, and this is what we pay our money for, right? But we can also notice, if we're a little bit more attentive to the details, we can see two minor trends as well. So we see this huge reduction from when we go from S1, scenario 1, that is the incumbent practice, to when we do just carbon capture and storage. And then we don't really see that much of a reduction. And then we see another moderate reduction here, and then no reduction almost at all. So what are these two orange arrows, and what are these two minor trends representing us? But the first one is carbon capture and storage, which we expected. And the second one is the elimination of steam curing. So what is this actually telling us? This is telling us that doing carbonation curing and mineral carbonation within in themselves do not actually, even though conceptually they should, in reality they don't really contribute to a lower emissions. So they don't really reduce our emissions, even though conceptually they should. So the added energy and the added transportation that we had are not are actually enough to reduce the benefits enough that we don't really see a meaningful reduction. Now, you might argue that there is some reduction that we seeing. What about that? Well, in life cycle assessment, we do a lot of assumptions, and those assumptions mean that small numbers like this, we really can't take them for granted. We really can't take them at their face value. So we don't care about small reductions, but we really want to see our big reductions. That's when we can say that a technology looks good or bad. But carbonation curing, of course, has potential if it can reduce, if it can eliminate the steam curing. But whether it can or can't do that depends on a lot of technical properties and a lot of technical procedures of how we're doing carbonation curing. So if that happens, yes, then we do get an emission reduction. So we just now concluded that we can't really use these two technologies to reduce our emissions. But what are they good for anyway if they're not good just for that? Well, we can answer that with another graph here. And this is an image that shows the fate of the captured CO2. The orange portion of this bar chart shows the geological storage. So we capture all of our CO2. In the first scenario, which is the CCS, of course, 100% of that CO2 gets geologically stored. And we can use some of that CO2, right? So as we use more and more CO2, that means we can store less and less geologically. So as we move to the right and introduce carbonation curing and mineral carbonation, we start splitting that CO2 between geological storage, mineralization in supplementary materials, and carbonation curing in the concrete itself, so sequestering that CO2 in the concrete itself. The point here is that these utilization pathways can be particularly valuable for cement plants where geological storage is either very, very expensive or it's just outright unavailable. Now, this doesn't mean that utilization can replace geological storage. We still need CCS for the bulk of our emissions, but it can reduce the reliance on geological storage and potentially improve economic in certain contexts. But then no LCA is complete without understanding the uncertainty. And the uncertainty analysis shows how key changes in parameters and assumptions that we've had can affect our results. And as you can see, the green bars are the assumptions that can go right for us. So in cases that we've assumed a certain carbon intensity with the electricity grid, but our electricity grid turns out to be much cleaner than we expected, we'll proceed towards those. Green side will move in that direction. And in the case where our electricity grid is dirtier than what we expected, we move towards the orange side. And as you can see, the orange side is much bigger. So what is this telling us? And this is most true for very concerning the carbonation curing. So what I want you to take away from this image is that carbonation curing, sure, it can decrease emissions if it can eliminate the need for steam curing, but it can easily lead to an increase in the emissions if we're not careful. So we really need to be careful what kind of electricity grid we're linking this to, we're plugging it into, and what is the exact procedure of the carbonation curing that we're doing. So takeaway messages that I want you guys to take away here. But the first one is achieving net zero we'll never get there without CCS. Like CCS has to be a part of the solution. It's just integral. Like without CCS, we don't really get the large emission reduction. There's no way around it, unfortunately. Carbonation curing and immunocarbonation do not reduce emissions on their own, but they can reduce the reliance on geological storage and potentially reduce costs in special circumstances. They can also reduce the reliance on geological storage. Now, the entire net carbon footprint of CCUS and the entire results of our LCA is really sensitive to regional conditions, particularly the carbon intensity of electricity grid. And this is more so within Canada, where the electricity grids are really, really diverse. But then this all is just one side of the coin. Another side of the coin is the techno-economic assessment, which we'll be focusing on further down the road. So what you just saw was the life cycle assessment, and then we integrate that into a techno-economic analysis, and we integrate them both into a geospatial model where we'll show how we can do decarbonization of concrete and what is our recommended way of doing it. But one of the advantages of coming up with this techno-economic analysis, and one of the tools that we developed while going from the LCA to the geospatial model is a decision-making tool. Now, this decision-making tool will help decision makers choose which decarbonization pathway their cement plant is best equipped to work with. And this is something that we've worked, and it's almost done. We're nearly at the end of it. So if you're a policymaker, if you're someone who is involved in that, we would love to show you a sneak peek of what we have going on. And if you're interested, please reach out to me or Sean or Dr. Sleep, so we can talk about that. We'd be very interested to get your opinion as well. And with that, thank you so much for listening, and I hope I didn't bore you too much. And yeah, so if you have any questions, please feel free to drop them in the chat, and I think I'll let Luisa carry on from here.
You're muted, Luisa.
Fantastic. Thank you so much. But yeah, no, thank you, Maziar and Sylvia, for the great presentation. We do have some time for questions, so please drop them in the chat. We also have a Q&A box at the top, and it would be, the more questions you drop, the more interesting the conversation will turn to. For example, we have one question there. Oh, actually, it's more. Okay, it seems limestone-free cement will be a huge boost, but any research I've seen in this area is at least 20, maybe more like 50 years away from being viable. Do you have any evidence of near-term solutions?
I mean, I can take that, right? So our nearest term solution is CCS, right? And SCMs and using those. But one of the reasons that cement is really, really attractive is because of its particular heap process, which is limestone is a huge part of it. So I'm sure there are going to be like some other forms of like cements sometime in the very far future where we don't have limestone. I don't think that will happen like anytime soon. But then again, at that point, it would be a cost-benefit analysis. Do we want to like do CCS and go that route with a limestone process, or do we want to ditch the limestone and go for a more expensive route? But so in the end, it depends a lot on what the cost of mitigation is and which one is more cost-effective.
Thank you. I mean, you talk about integrating different methods to decarbonize concrete, but we also have a question in the chat about what about using direct air capture or biochar? A lot of questions through the registration page mention biochar, using biochar as an aggregate. But what do you think about this to decarbonize concrete and building materials? Are those viable options? to decarbonization?
So if it's okay with you, Sylvia, I'll take this one as well. So now, using direct air capture is generally really, really expensive. So that's just one thing that I need to put out there. So we would mostly prefer to use carbon capture at a cement plant and use the CO2 that we captured from the cement plant as opposed to from direct air capture because, well, it's cheaper. But then your question has two parts, which is the biochar. Now, I'm not sure how you mean to implement the biochar in there. And I'm guessing because Luisa mentioned that we also had another question related to biochar about putting it as aggregates. Now, the thing about aggregates is, well, aggregates are really, really low carbon footprint. They have really low carbon footprint. So instead, so if you ever want to replace aggregates with any other material, you have to have one of the two properties, like you have to have one of the two properties for it to work. Either your aggregate should be elevating the mechanical properties of your concrete in some way where you can reduce the amount of cement that you put in. So I don't think this is the case with biochar, but I don't know much about like what the biochar is going to do in concrete. But let's say that it magically can make your concrete stronger, but in that case, you will get a benefit from reducing your cement that you put in. So indirectly from your biochar, but replacing aggregates won't really give you that much of an environmental carbon footprint, except if you have this biochar and like bring its own negative emissions or something from itself, from its previous life cycle chain. Sylvia, is there something you want to add?
Yeah, if I could just add a little bit on the direct air capture versus CCS for cement decarbonization. I think in most instances, carbon capture and storage in an industrial source like a cement plant will be less expensive than direct air capture. There can be instances in particular deployment situations where you have, very limited proximity to CO2 for geological storage, where direct air capture might start to become competitive. But you're really sort of at those more extreme cases where you're having to transport your CO2 a very long distance, or you have a very extremely high energy cost or that kind of thing.
Well, thank you both. We also have a question on what's the highest supplementary substitution volume that we can accomplish. Pretty much the supplementary cementitious materials, if I'm not wrong. What's the highest percentage that we can reach?
So there are different. So we have many different SCMs. We have fly ash. We have GBFS. We have microsilica. So we have all these, and calcined lime, and we have new startups that are coming up with their own SCMs. And so in each case, it would be different, but there are reports, unconfirmed reports. Like there needs to be a lot of testing and a lot of regulations around this. But I don't think in Canada, but in other countries, like in Mexico, I think like you might see something as far as like 30%, 40% reduction in clinker. So that's the percentage that you might see there. But in Canada, it's less. So I would say like in the realms of like 20%. Is what we have as comfort.
Thank you. We have okay, just building on that on the answer that you got there. I'm gonna ask first one question that we got through our registration page on particularly just emphasize like what are the key techno-economic and research considerations that need to be studied to better inform CDR regulation.
I'm sorry, Luisa, I didn't catch that question. Sorry. What was the question?
No, that's okay. Like, if what are the key techno-economic like, or what's the key research that need to be considered now so we better inform CDR regulations? Besides what you mentioned that you're going to be working on the future, what other considerations of research we need to move this forward on the regulation landscape?
What do you from whoever asked that question, what do you mean by key techno-economic aspects? I mean, essentially, we have like two really big aspects, right? So I'll try to answer it, and if you think you're not satisfied with the answer, please do feel free to reframe the question in a way that I can better understand it. But there are really two sides to the problem. So we have the mitigation and how much CO2 reduction we can get from each technology and each pathway. And on the other hand, we have the costs, right? So the two metrics that we have is, well, how much reduction can we get and how much would it cost us to get to that number? So those are like the really key questions that we should be answering, which, well, if we're talking about like TEA metrics, can be put in one metric of the cost of mitigation, but then like that's what I think about this.
Okay. And Kathy asked here, curious about your view on the role of policy in ensuring that CCS is only used in hard to decarbonize industry like cement without delaying transition to clean energy industrial spaces.
I think the policy people are better equipped to deal with this question. But Sylvia, do you want to take this?
Sure. I'm not sure we can speak on behalf of Cancor, but I think it's it's a risk, right? And I think we're really focused here just on concrete and cement, where we think that there is an opportunity for CCS, where it really is the lowest cost option, and we don't have other opportunities or other mechanisms available to us. But that is a risk to broader CCS deployment.
I just want to add one thing, since we're talking about like CCS and unintended consequences in a way. There is a very subtle underlying consequence to doing all these processes, and not just CCS. Even when we talk about these supplementary cementitious materials, these cement replacements, even when we talk about them and when we talk about their manufacture, and we really expect that replacing 20% of cement with this other material will lower our cement production and in turn lower the emissions of the cement production. But you really need to be also thinking about this fact that most cement plants will just have like a new blend of cement with that a CM added in. And instead of producing, let's say, 1 million tons per year, they would be now producing 1.2 million tons per year. So that in itself is an unintended consequence of producing those SCM. So sure, I think we also need some regulations, but then that's not really my place to talk about those regulations.
No, but thank you for providing insights on that. So like following on now going into more of the technical part, if you're applying all the three technologies you mentioned, is there any sequence of application? What would be the interactive effects of applying more than one solution? And they put an example, for example, like could mineralization impact CCS efficiency? So is there like a best practice balance with the use of these technologies?
Yeah, let me talk about that. That's a good question. Well, in our technologies and how well, some of them work together and offer co-benefits to one another. For example, doing mineralization and adding SCMs also increases the natural uptake in concrete. But I wouldn't say that minorization would impact CCS efficiency? No, because well, we would do CCS first, or mineralization first, and then whatever's left, we would just do CCS. But it might impact it on a economies of scale level. So, for example, like if you have these new options that are like going to be alternatives to CCS, it might impact you in the way that, well, now you don't have to transport as much, so you might opt out of developing these pipelines, which might in turn lead to an underdevelopment of CO2 pipelines. So in that case, like if you go down that rabbit hole, I guess maybe. But no, I don't think it can affect the CCS efficiency. And I think there's another part to your question, which I can see. What are the interactive effects of applying more than one solution? So I talked a little bit about that. And we also had a scenario where we did both mineral carbonation and carbonation curing. And again, while conceptually those lead to a lower carbon emissions, well, in fact, they really don't. So it's really more about what we're getting out of this. So we can have that effect by applying one or two or other utilization techniques. We can reduce the need for geological storage, sure. But in terms of the CO2 mitigation, then no, the real benefits come from somewhere else.
If I could just add to that, I think you start running into problems of cost effectiveness when you layer all the three technologies together, and while you might get some marginal additional GHG emissions intensity reduction, you end up with concrete that's so expensive that you're starting to get, outside of the realm of what's practical to deploy for the emissions reductions you achieve.
Okay. While we wait for other questions coming, we do have some that were on the registration page. If you could speak a little bit on, what role could standards play on the effort to decarbonize concrete at scale? Any suggestions for people that is in that realm?
Yeah, so standards are actually really key here. We just saw that how if we don't really take into account what happens further down the road, carbonation curing can have this exaggerated benefit, which is, so we really need to be very, very careful on how and what are like our assumptions going into that and what are we assessing. So it definitely needs to be a key area of focus. We need to make sure that we get it right. But again, on the standards and policies, I don't think I'm an expert that I should be answering those kind of questions.
Okay, no, thank you. No, but this is the great thing about the Concorde, and then having people from multiple disciplines, and then see, okay, maybe you have some insights on how can we help each other. But thank you. Do you guys have any insights on how Canada is doing in CCS and other technologies to reduce carbon footprint regarding, of course, the using concrete?
Sylvia, do you want to take this one on Canada's? How can I just can say that I know that some cement plants are talking about doing CCS and they're considering their options and probably, but I think Sylvia is better equipped to answer this question than me.
Yeah, I think there are CCS deployment projects for Canadian cement plants in the works, I think. But it's a long way from, full industrial decarbonization.
Yeah. So we have a follow-up question on the technical question you answered earlier on the distribution of the methods. But yeah, building on that question about sequencing, based on what we know about price per ton abated for each method, is there a risk that a suboptimal point is achieved if operators select the most cost-effective abandoned solutions first?
Yeah, thank you for asking that question. That's actually a very technical question that I didn't think anyone would ask, but yeah, of course. So what you're referring to is actually a metric called regret in techno-economic analysis. And well, in fact, our decision-making tool take this into mind. So we try to come up with solutions that not only give you the most optimal solutions based on your regional conditions and your context, it also ensures that you would have a low regret, which is exactly what you're saying, choosing what is to be optimal based on the analysis. So the analysis might tell you that, well, based on these regional conditions, this is the optimal pathway to choose. But then again, within those conditions, there might be an outlier that will fall through the cracks and will leave you with a high regret. So this is again something that we actually address in our next part of our work. So please, if you want to know more about that, stick around and tune in for future webinars. So we would love to show you what we've done with that.
Yes, thank you, Maziar. Yes, we'll be having some upcoming webinars every 2 months, so please stay tuned for those. Again, I'm just gonna, if there are no more questions from the audience, please have a couple of minutes if you have any other. But one last question that we have is if there are some cost estimates or challenges that might hinder the ability of for decarbonized concrete to be a competitive commodity. I know this falls out of the technical aspect, but if there's any insight.
Yeah, sure. So in terms of the cost estimates, there are some cost estimates, both other in the literature and the cost estimate that we've come up with ourselves. But so cost estimates are out there, but what is going to eventually stop this from being cost effective or not depends a lot on how the policies form around decarbonization, because essentially doing anything, any efforts for decarbonization is going to have a cost. It's not going to be as cheap as the concrete that we have right now, right? So I guess it's more of a policy solution and how policies are going to make that happen. Sylvia, maybe you want to add something to that.
Yeah, I saw some interesting work recently that looked at how big of an impact does an increase in the cost of concrete have on the overall cost of an infrastructure project. And actually, infrastructure projects like concrete, well, might be expensive, overall, and it might have a big impact deploying CCS on the overall cost of concrete. When you look at that over the cost of, say, building a bridge or building a large infrastructure project, this ends up being relatively small. So maybe an infrastructure project can likely absorb more of a cost increase in the cost of concrete per ton and dollars a ton than you would typically expect, just because it is such a small component of that final project cost.
Thank you. Just Master, if you don't mind, like just flipping to the last slide, because I do want to emphasize that we have more webinars coming up in 2026 with different. We're going to be talking about different topics, including listening from the research, from the political science aspect of CDR. So please stay tuned. We'll be posting soon what's it's going to be about. If there are not any more questions, I'm going to close it here. I want to thank you both, Dr. Sylvia and Maziar. Thank you for a great presentation and tackling all those questions. I look forward to seeing the future work that you mentioned. And with that, I'm going to Carson will say unceremoniously end the webinar. But I hope everybody has a great day and hope to see you in the next webinar series. Thank you.